Hi everyone, and welcome to the first episode of Powering the AI Stack. I am Barak Turovsky.
And I'm Ilya Tabakh.
And we are very excited to start this series that will explore very interesting and, in our opinion, a bit underappreciated aspects of powering the AI stack, which obviously everybody talks about it, and obviously previous month was amazing about announcements across the board. And basically, we wanted to start sharing from our experience working on those topics for many years. For example, in terms of my background, I seem to joke that I worked on those quote-unquote esoteric technologies like large language models way before, 10 years before maybe, when they became hottest thing on earth. I was the product lead that productized first LLM with Google Translate, participated in developing BERT technologies and transformer technologies in Google Search and Google Ads and other places, and I'm currently VP of AI at Cisco.
Awesome. Yeah, and I've played in all kinds of different parts of this ecosystem, from kind of the computer engineering, computer architecture side to deploying modular data centers at various parts in the power grid and doing blockchain services and sort of weird computing things. And then the last several years I've spent at a large engineering company learning how utilities and industrial users ultimately do new things connected to many of these resources. So it's kind of a superstorm of these things in this conversation, which is great.
Ilya, why we're starting this conversation, and also why we're starting it now?
Yeah, it's kind of the timing and the scale of these things. Computers have been around for a long time. There's been a computer on our desk or in our closet for decades and almost a century at this point. But the scale at which these things are happening, in the last 5 years, the tech companies have spent more capital on infrastructure for data centers and computing than the oil majors have for kind of power and energy. And that kind of brings what's happening into a completely different level of kind of engagement and activity. And because of that, you have to have kind of more perspectives and more experience because it's kind of frames up a much more complicated and more interconnected problem.
Yes, in addition to being interconnected, one thing that we discovered in having multiple conversations in different forums, that actually the biggest, in our opinion, underestimated aspect of it is that people don't realize the pretty significant timeline mismatch on planning and delivery of different components in the stack, and this entire stack across demand and supply. So we created this framework of powering AI stack that we call 4Cs.
Yeah, absolutely. And what's cool about the 4Cs is the fact that because of all this complexity and interconnectedness, you have to just organize all the noise, right? And as Barak and I were talking about it, we've been able to break it down into a few different categories. The first one is consumption, right? So many of us are at least aware, if not using all the various models, right? And so that individual consumption, how our enterprises and SMBs are going to use these models, and then ultimately what other applications, whether it's in autonomous driving or others, will force us to think about what are the requirements, how much infrastructure do we need, and so that really drives everything at kind of the demand level. Then there's kind of the cognition, right? What models are there? What kind of data sets? Is it text? Is it video? Right? There's a lot of exciting developments going on. I mean, in the last year and a half, we went from everything essentially being text-based to not. And that's been kind of exciting to watch.
And last couple of weeks, we had huge DeepSeek moments related to that part as well.
Oh, absolutely. And what's crazy is it's a moving picture across many of these. The compute area is really thinking about the TPUs, the GPUs, the custom hardware sort of at the hardware architecture, as well as the rack level. And so how do you organize these things in order to be efficient and deployable and scalable, things like that. And then ultimately, all these things are connected to the grid, to infrastructure. And so there's kind of this capacity side. Where does the power come from? What about water? And then kind of even the buildings are, kind of becoming these large industrial complexes where before it might have been the size of a large warehouse, right? And now these are becoming significantly bigger than that. That really helps us kind of organize and think about who to even bring to the table to think about these issues.
Yes, and basically going back to this timelines mismatch, the key to understand is that there is a very different planning horizon in terms of demand. The AI application, the demand is extremely fluid. And to be fair, we are in a very early stage of this wave of AI revolution. Nobody knows which use cases will become big and how big they will become. So demand will fluctuate. On cognition, on model side, we see a lot of excitement. Models become more efficient, smaller, bigger, etc., more capable. But at the end of the day, it's way easier to develop those models than it was before, or fine-tune those models. But it's probably a planning cycle of months, 6 to 12 months, right? But then you're going to way more complex portion, and some of it I discovered 10 years ago when I was developing the first LLMs that actually compute to put, not to mention develop new GPUs, new chipset, but even to put them in the data center, put them in physical racks, it's a planning cycle of years, right? It starts from 20 to 48 months, and we all experience it today on demand side. Getting GPUs from any cloud provider today, if you need the H100, it's hard. And then I think the real kicker for me was that even me, who was working on it for many, many years, got educated by Ilya that on the physical side, on capacity, on electricity, power, water, the capacity, the planning cycle is, if you're lucky, is 4+ years, and in many cases the planning cycle is decades.
What's crazy, and the way that we're going to kind of structure the series is really thinking about bringing in folks and experts with kind of boots on the ground experience. Who's actually designed and delivered hardware, who's racked and stacked and kind of interconnected these things, and who's really leading the conversation on, what are the data center campus model and sort of these various evolutions of the traditional data center and hyperscaling models look like. And that's going to be an important kind of consideration to go forward, because Barak and I both have stories where, we thought we knew how the world worked, and then we had a lot of surprises on, hey, there's a lot of gotchas. And a lot of the gotchas, before we actually figured them out, we didn't even know it was a thing. And so I think that's really important. Barak's got a lot of experience on the consumption and cognition side. So what we're going to do is spend a little bit of time diving into both sort of a topic, a little bit of time on understanding the challenge, and then also maybe think a little bit about historical perspectives and things like that.
Sometimes I feel a little bit like an elder, quote unquote, because I worked on, it's such a young industry, and Ilya had the same experience on his side. Because it's such a young industry that's moving so fast, people like myself who worked on it for 10 years have stories that sound like a story from 200 years ago. It's just unbelievable. But yes, basically on the demand side, we were working on productizing the first, what we now call LLM. At that time, we called it Deep Neural Network. In 2015, 2016 for Google Translate, we discovered all the issues that we're discussing today, even last week. We discovered that inference is extremely slow, right, at GPUs at that time. That's what led Google to develop TPUs, led Google to actually go to the compute side and do something there. We discovered that you actually need to shrink the model. We basically did the distillation that a lot of people right now talking about it in the topic of DeepSeek. So we basically work across consumption and cognition and compute to try to bring all this together to launch the first LLM, because, our latency was 100x slower than our production system. It was an unusable system, right? So, and that's where we actually start discovering some of the things, because I vividly remember the discussions. Oh, guys, we have, and Google, everybody's so excited about it. We want to deploy those TPUs, tensor processing units. Why can't they deploy them faster? And I got this a little bit education. I also got this cryptic statement from one of the leaders at Google infrastructure that the ultimate measuring unit in compute is power. And I'm like, okay, sounds interesting and cryptic. I didn't really understand what it means. To me, it was like, yeah, it's like, electricity grid. So it will always be there. And then Ilya probably can expand a little bit. Ilya basically educated me. It's not even close to that. You cannot assume it will always come and you can increase and decrease the capacity of electricity.
Before we jump into that, actually, I'm curious on, kind of from launch to scale, like what were the big moving pieces, because a lot of the things I see folks doing today are testing models, training, really thinking about what do I get to the point where I can click go.
Yeah.
And that's where you get into a lot of the scaling conversation. So maybe if you could spend a second on that.
Yeah, that's a great question. By the way, one additional thing that gives us a lot of hope, I don't want people to get into perspective, a lot of the things is timelines are set. There's a lot of things you can do to optimize, and we saw this DeepSeek moment. We had something similar on that front. So I actually want to share two examples, both optimistic and let's call it cautionary example. First thing, when people are excited and work together as a team, you can drastically reduce the time to market. So we planned to launch the models that will be in production for the first language in Google Translate within 3 years. So basically in 2018, when we start 2015. But there was so much excitement and so many amazing people like Jeff Dean, who helped us on infrastructure, physical infrastructure side, that it only took 9 months, right? But it was an extremely complex project because remember, a lot of the things now became way better because amazing things that OpenAI and ChatGPT and Google did, that they democratized access to models, right? We had to develop those models from scratch with enormous amount of data and enormous amount of things that you need to actually productize them. But as I mentioned, one of the things we struggle with, and we are struggling with that today, is that latency, right? Latency was extremely slow. On GPUs at that time, and just to give people a historical perspective, that was a 6 billion parameters model that is currently considered small. And I always correct people, there is nothing, terminology-wise, there is nothing small in LLMs. It's large, humongous, and gargantuan models, right? So we had to deal with a 6 billion parameters model that was 100x slower than production. That led Google to actually develop their own custom chipset called TPUs, and we had to deploy it very quickly, right? And as I said, the only thing that made me think about data center was a cryptic statement, I believe, from Urs, who said the only measurement in data center deployment is electricity. I didn't really fully understand what it means. To me, it's like, yeah, you turn it on and it works, right? But that's basically, and thanks to Ilya, in our recent discussions, you educated me about what it actually means.
Yeah, and the cool thing there is data centers have actually been focused on kind of the power utilization efficiency, the PUE. You know, infrastructure generally is hard to observe and hard to control, right? We've been talking about IoT, so, you know, kind of the Internet of Things and interconnected infrastructure. But one thing that's nice about a data center installation is that they typically, you know, are organizing around this concept of how much power is actually going to the performance of the compute. And because the power consumption is going up to, you know, be such a large part of the operating footprint of these large facilities, they're starting to kind of slice, and in many cases have already been kind of slicing what categories is, you know, in the compute is that happening? Is it on the network? Is it actually on the chip, you know, kind of GPU level? And so it's great because in the hardware and really like heavy infrastructure world, that hasn't been possible as much. And so that's great. What about the sort of kind of that interaction of the model data, you know, kind of the compute side before we jump too far into kind of the next category?
Yeah, so I think I also want to give people cautionary tale. Everybody, especially on investing and Wall Street, will tend to jump to conclusions. Oh, we need huge models. Oh, with DeepSeek, we don't need huge models anymore, and we don't need it's all way more complex and interrelated. So just to give people a cautionary tale on this DeepSeek moment, we actually had something similar when we launched Google Translate in 2016. It obviously made a huge wave. There is actually a very good article, The Great AI Awakening, that maybe Ilya or I can post and people can read. The first wave of AI that I was lucky to participate. But at that time, we basically announced and announced also that we launched it on TPUs, on custom-built hardware, and we were very proud about it. And then Facebook decided to take a very different approach. They decided to be very efficient, and they launched, I believe it was called Open Compute Alliance or something of that sort. And they actually published a very influential paper that showed that they actually trained LSTM model for translation on CPUs. And that's like, you know, a small fraction of the cost if you versus using GPUs, not to mention using TPUs. That was a little bit of a code red moment in Google. We are hearing about code red and, you know, OpenAI and Facebook, and we started to look at it, and we actually were impressed about the results. It made us question our strategy. Do we really need custom TPUs? But what we discovered, and actually who discovered it even more, was Facebook, that basically underinvested in custom chipsets that currently everybody is investing. That what they discovered is actually maybe applicable to one use cases, but not to many others. And if you rely too many on saying, oh, DeepSeek will solve all our problems, you will miss that for some use cases, DeepSeek might actually not be a good use case. It might be good for reasoning, but might not be good for, generative AI, etc. And then if you wait, if you don't understand it, because of those cycles, the moment Facebook woke up and said, hey, we actually need custom chipset, the planning to develop it, it's years, right? And if you now need infrastructure to power it, it might be, you need to commit now to deploy it. It's like one of the things Ilya and I were talking about, that like there'll definitely be enough power, but not necessarily when and where you need it.
Actually, to dig into the compute side a little bit, right? So we're kind of talking about the requirements for the application in the individual sense, and then the aggregate of all of those to where do they run. Most of these sort of footprints have not specialized yet. There's been conversations about edge data centers close to kind of the user for very low latency applications. But that's still sort of an emergent space. But it's cool to see how we're already talking about, hey, this is the problem I'm trying to solve, right? These are sort of the model tools and sort of the requirements of the computation. And then there's sort of the, physics still tells us that it takes a certain amount of time to get for a packet to get from one physical location to a different. So we're already kind of seeing the interplays. As you start to think about, deploying these resources and compute units and things like that, the hyperscalers have already done a lot of work in getting to the 50 and 100 megawatt level, right? The cloud, we're quite a ways into that transition. We're not done even with just the kind of e-commerce data cloud yet.
Ilya, what does it mean? Give us a perspective. What does 50, gigawatts means in terms of, powering, a small city?
Megawatts. So 50 megawatts is a lot. No, but it's, it's crazy because we're talking about, orders of magnitude from a GPU taking, hundreds of watts to a rack, today taking 20, maybe 50 and kilowatts, right? So that's already an order of magnitude.
Is
right?
it like multiple houses? Like what does it mean in the equivalent of layman people who are like...
Yeah. So if you think about a small city, right, we're talking about like 100 megawatts. And it sort of depends what kind of industrial applications and things like that. But if you turn everything on in a standard American house, we're talking probably 8 kilowatts, right? So one rack running is using more than a typical, and typical is every geography has different on typical as well, but that's sort of the order of magnitude, right? And then if you think about 100 megawatts, right, that's pretty sizable. That's like a small city footprint, right? There's some campuses that are being proposed for, a gigawatt and up to multiple gigawatts. And, there's other industrial applications that also have demands on that level, but you're really talking about, pretty significant amounts of power. And so as, we think about the compute, as you start putting more than 50 kilowatts in a rack, right, which is not quite a subdivision, but, several houses, you stop being able to cool that with air in kind of the traditional way. And so the other thing is, as these densities and things like that pop up, there's a lot of dynamics that happen. And then ultimately, the availability of the resources that you need, whether it's power, land, the buildings themselves, or, water capabilities and things like that, are all a moving target. And they're all different in sort of different areas. And so in places where there's already a lot of industrial and data center activity, there's probably not additional available power sitting around. And then the other part, and we'll get into this in sort of subsequent episodes, so I'm not going to give you the full rundown.
Yes, that is very useful even for me, as I say, I consider myself elder in this space.
Yeah, no, for sure. But like, what's interesting is utilities and sort of infrastructure type players make decisions in 5-year and 10-year windows, right? And the other challenge here is it's awesome to have net new demand, right? But if you don't know that, hey, this net new demand can commit for 10 years or 20 years, or, an energy asset may be a 30-year deal, right? And so one of the challenges is that it's not completely clear yet what an AI data center, A, what that even looks like, and then B, what the load curve, essentially what the power demand from that looks like. Is it flat all the time? Can it be dispatched? So can the grid say, hey, can I get you to turn off for an hour because it's really important time on the grid? And that conversation makes it even harder to sort of plan and understand how.
Yeah, that's basically, we want to bring home this notion of time horizon mismatch. That to us is the crux of it. And as I said, me coming from demand and model side had a blind spot on the capacity side that I'm very excited to have a discussion, vice versa. Ilya, who understands deeply as a part of compute and capacity, is very interested to have a discussion about how demand and models will shape up and how they will impact those planning cycle. And you need to start planning yesterday to actually get to something interesting and relevant to power it.
Yeah, and what's crazy, so we've kind of gone through one pass, kind of consumption, cognition, compute capacity. We've kind of framed it up a little bit. But because it's such a kind of first order actor in sort of our industrial and power capacity conversation, it gets to a place where we can start to think about, what are some historical parallels and things like that. And so, in some cases, there's quite a bit of competition and demand for things like GPUs, right? And so Barak likes to bring up the oil shock, so maybe this is a good time to sort of talk about that comparison.
Yeah, first of all, a lot of investors don't think there is a lot of competition. They think it's all NVIDIA world, which I think will, it will evolve, right? As I say, there are a lot of parallels even from my time at Google Translate, where people were considering using CPUs, and for some applications might work, but not for others. But yes, going back to, now a lot of people like, we can short NVIDIA because we actually don't need all this demand, and we don't need this, the Stargate project or whatever people are doing on energy. We don't really need it. It all will be super free and cheap, etc. So my great example is the oil shock of 1973, right? People overnight went from plentiful, abundant, and very cheap oil to, oh my God, gas stations, huge lines. And then, but one thing I wanted to mention that people understand, since then, we are talking about, almost 50 plus years, there was a huge focus on energy efficiency. Every country, every region did their own thing. Some countries like French invested in nuclear energy, some other invested in public transportation. But if you look at like energy consumption, especially for cars, it's way more efficient than it was before. Also, the demand changed a lot, right? The cost of consumer goods fell by a lot, which impacts the margins. But guess what? On the very basic level, back to Urs from Google point, the ultimate measurement is unit of energy. Did the price of oil went down? No, right? There will sometimes shocks and they dropped a little bit. The price of oil continues to go up, right? So we should, in my opinion, we should assume that the price of energy will, because of the planning cycles and because you'll probably be in situation of misaligned demand, it sometimes could be, we have too much. And then you underinvest, but because it's like, housing, right? It's like you need to make a decision today. I think we'll constantly be in this situation of misaligned demand and supply. And it will always, in my opinion, long term, we'll continue to see that the price of unit of energy will not go down and will actually make it more complicated. And Ilya, I think you had your own interesting examples more on the supply side, right?
Yeah, well, a couple things there. First of all, let me pull on your kind of oil analogy.
Yeah.
Everybody thinks of sort of, to follow the analogy, oil price, energy efficiency, so fuel economy essentially for a car in a passenger car, right? And so the analog for that in the AI space is a generative AI text model or maybe a multimodal model running on a GPU and then ultimately being served through either an app or a web API endpoint. Exactly, right. But for oil, there's also cargo ships. And there's also sort of other applications with other form factors, with other sort of derivatives. And so it's interesting to think about, what's the cargo ship of AI? And ultimately, kind of, what does that ship look like? What is needed to, kind of make that operate? And then, for oil, there's all kinds of edge cases too, right? Smaller applications. And so as we really have that conversation, even we haven't really figured out the oil car equivalent for AI.
Yeah, demand, we don't even know how demand will look like. By the way, it's the same, the demand today that powers oil is very different, right? The prices are different, the type of applications, type of use case, everything. Cheap, oil, plentiful oil gave rise to a lot of use cases. In that regard, cheaper, more efficient model, which I do believe will be the future, will give rise to more interesting things. But at the end of the day, it all comes back to something needs to power it, right?
Yeah, well, and then the other sort of example that I had is when we were operating a modular data center company, we really looked at this concept of kind of interruptible bulk computing. Right. And we were serving multiple different markets. We were doing some blockchain services. We were supporting some energy trading folks that were running kind of, heavy mathematical algorithms. And then we were doing some video rendering. So think of like 3D Studio Max when you render videos and things like that. And what's interesting is that the sort of margin expectations and sort of use patterns in each of those markets changed very differently. And so initially when we started, power was like 10% of our cost stack because we sort of had other operational issues and things like that. And so when we were thinking about, hey, this is a modular unit, we can move it in weird and different places in the energy grid, whether it's behind the meter at a renewable energy site, or things like that. But there's trade-offs, right? Because the nice thing about the grid is it gives you firmed, reliable, consistent power in most cases. And that's not how behind the meter at a wind farm would look like, right? But how quickly sort of that margin and that expectation for each one of the markets we serve changed, and thereby, how quickly we had to sort of think about, is this still kind of a viable approach, was surprising how quickly it developed. And we were thinking about the area and kind of thinking about what's the offtake, what's the margin, how does the business model work. Power was an important component, but power was pretty flat and available and steady because we geographically went somewhere where there was a lot of wind coming toward population, right? And there's sort of places like that around the US. But it's just crazy to think about sort of this demand and consumption. And folks are right now kind of making pretty long-term commitments on the hardware infrastructure side, and in many cases, much longer than they're used to, right? And then this demand and margin and all those things are still kind of moving targets. So it's going to be interesting to see how all of that develops in parallel.
Yeah, and it's a great point because at the end of the day, again, people going to extreme, going back to oil shock. Oh, huge line for GPUs. Instead of like, sorry, we're out of gas, it's like, sorry, get in line, 1 year commitment minimum to get H100. And that will probably, that will adjust itself. And I think supply will fix itself and we'll have more steady supply. But it doesn't mean the cost will go down significantly. But on the flip side, the cost on the demand side might go down significantly. People will expect way cheaper cost of models. By the way, most likely even today, those business models are heavily subsidized, right? And all those companies are doing huge investment, hyperscale, huge investment, capex investment, 75, 80, 100, 500 billion. That needs to be recouped somehow. So I think the margin aspect, and let's face it, not everybody has amazing business model like Google, Facebook, and Microsoft. Cost structure, margin structure will be very different. And if because of this mismatch or planning cycles, cost of electricity even stays constant, right? That's a pretty big challenge as well, right? So that's part of the things that we wanted to unpack and understand on each component, what we could see, what we should plan for.
And so we mentioned a couple of historical contexts. There's probably others that we can jump into, but a lot of them, as we were thinking about it, we're talking about how do you have to make investments in supply, and then how well structured and understood is your demand, and sort of both success stories and less successful stories in the mismatch between those two. And, sort of getting back to why are we having this conversation is I think there's a lot of different paths forward on, how demand will be structured and how supply will be delivered. And there's probably different options in the, 1 to 3 year window, 3 to 7 or 8 year window, and then sort of 8 plus, maybe 8 to 15. Right. And so it's really important to kind of increase the number of perspectives there.
Yes, and just to add to that, because it's so interrelated, I want to make sure people understand there will be huge freedom of innovation and huge impact for innovation to make everything more efficient and cheaper and plentiful, etc. Again, using the historical parallels. Imagine yourself, nobody would invest in more efficient cars, right? Where the price of oil will be today, right? You definitely, even with that, we are still in pretty, rising price of oil, more or less. But imagine yourself, you would not make those huge investments. So I think the key for us, because it's such a complex, interrelated topic, is actually bring experts in those areas and explore what could be done, but also understand to be prepared for it, because the timelines are very different, right? Like whatever is decided today on nuclear power side might take years to bear fruit, right? And that's what's very important to understand.
Yeah, no, absolutely. And actually from the chat here, Ryan suggested a good way of thinking about scale. If you think about kilowatt, megawatt, gigawatt, right, kind of orders of magnitude, the K is, roughly your kitchen, right? Your oven is probably 2 kilowatts. The M is like the size of a mall, right? A typical mall in the US is probably taking a few or maybe low tens of megawatts, depending on kind of what's in there. And then the G is kind of grid level, right? So a power plant, a large solar plant, or potentially a combined cycle natural gas plant, you can be talking about hundreds of megawatts or gigawatts at one site, right? And most utilities have a fleet of power generating assets, right? And so it's a collection of these things together. And so
that's great.
As the gigawatt, as the data centers, cross the gigawatt mark, right, and talking about going into multiple gigawatts, it really does make it sort of a grid level consideration. So thanks for that kind of analogy.
No, that's great insight. Ilya, I think we should open up the stage for additional questions or suggestions. What do you think?
Yeah, absolutely. So we got the comments open. Folks are kind of commenting and jumping in, and I'm kind of bringing that in. I think maybe one thing to do as we encourage people to kind of ask some questions and give us some perspectives is to just walk through the sort of key blind spots, right? One of the things that we were kind of talking about in the preparation here is that, and it was actually one of the things I hadn't thought about, but in all of this stuff, there is sort of an energy intensity and sustainability lens as well, right? And so as organizations and individuals adopt AI models and things like that, there's, sort of this concept of scope 1, scope 2, and scope 3 emissions. How much carbon is generated for your use. And it's not well qualified yet, or quantified, I should say, on kind of what the carbon intensity. I think the hyperscalers are actually doing a good job. Most of them have a sort of sustainability goals in 2030 or 2040, kind of net zero by then, or in some cases, carbon negative. But, the pace of adoption and deployment here and sort of the current power options is definitely making it more challenging to think about how to be able to deploy the demand and supply. So kind of thinking a little bit about that, energy consumption and carbon intensity oversight is important.
Ilya, just for my own education, does that, at least in the short term, increases cost of basically delivering unit of power if you take sustainability goals into account, or that's actually in the longer term decreases it?
It depends on the technology and sort of depends on the requirements. But currently, the things that are, kind of most obvious and available would increase the cost of lower or,
Which
same
obviously
carbon.
a complicating factor, at least in the short term, right? It's like
Absolutely. But that's sort of the trade-off is, because you have a generating fleet, and depending where you are, there's different availability of renewables. The price of batteries is changing. And so it's hard to make, kind of definitive statements for here's your best power option. And part of the challenge for the tech companies is, and really any large consumer of electricity is thinking about how do they self-generate, buy renewable energy, and then ultimately where do they connect on the grid to, maybe there's a good hydro availability or kind of other places where the carbon mix of that area geographically is different. And so this all goes into sort of the planning exercise and the mechanics of site selection and thinking about how do you kind of expand your fleet.
Yeah, excellent. And again, as I said, the reason I'm excited about it, I myself will learn a lot even from this session. And obviously, as we bring experts from different areas, we'll all hopefully will learn, and it will be very helpful for all of us. Across, AI practitioners, investors, data center operators, data center planners, etc. Everybody, because we're talking about the entire stack and interrelations between different components. I think that's why it's so exciting. And I'm really looking forward for a future episode.
So we have, it was a matter of time, but Mikhail from the chat asked, how does DeepSeek change the energy demands? So I feel like let's do it. Let's go through kind of the thought process.
So, I mean, I mentioned some of it, as I said, two things. People should not immediately assume all AI applications now we can run on efficient models. And by the way, as I said, feeling like an elder, I was talking about some of those topics years ago that, there was a big fundamental discussion. I personally had a discussion with Ilya Tabakh at some point when he said, it's all big models, you cannot build, a rocket ship in a backyard. And I said, yes, maybe it's true, but for a specific narrow domain, and let's face it, most of enterprise applications are not necessarily for a big domain like search, right? It's not every topic. You can go, I always believe the future will be you take the cost of developing the model from scratch dramatically went down when you have open source models like Llama and Mistral. So you take that and you fine tune it with data, and you can get a very efficient model both in terms of relatively cost and as well as latency, right? So I think to me it was actually given, using the example of Allshock. It's given that we need to have more efficient engines. But that's to me because demand will fluctuate and will actually grow. The faster models you have, you'll get way more applications. Hey, tomorrow, government will decide that they want to build, hordes of autonomous drones. That's actually happening. And they need smaller models. Some of them be on device, but many of them will require a cloud connection. So all those things will probably drive demand high. So I wish we could say, and I think a lot of Wall Street analysts would want us to say, oh, demand will go to zero, right? Or demand will go to the roof. And it's very easy, but in many cases, it's way more complex. And it's very important to understand in each component what innovation is coming, but even more important, what is the timeline for this innovation to hit the market? Because an AI application could be tomorrow. On a model, it could be in 6 months to a year. But you probably can expand on that, but anything related to compute and especially capacity, even if you have innovation today, it needs to start to be deployed yesterday to actually hit to be relevant in a couple of years from now.
I think that's true. And I think that was sort of my point about making what's the efficiency of a car versus a cargo ship.
Exactly right.
Because we haven't seen any AI cargo ships yet.
That's
right. And so thinking a little bit about the NLP, sort of the language Gen AI use case, DeepSeek makes sort of the processing and the training cost slightly less.
Yes, well, it could be a lot less, but please understand it's only training, right?
Right.
Inference depends on the use case and what do you need. B, as I said, nobody can right now say it's very new model. There's already people saying that some of there are limitations, using the example of Facebook and training LSTM models for translations on CPUs that showed I literally, as I said, feeling elder, I feel a sense of deja vu. It was literally the same moment. Oh my God, we invested so much in TPUs and look at this, results are comparable or maybe even slightly better for a little bit. What have we done? Do we really need those TPUs? Well, I guess not only we need it, everybody, including Facebook, went entire 180, and now everybody who was actually part of founding members of that alliance, I think Microsoft was there, Amazon was there, etc. Nobody at that time thought that custom chipset is important, right? Because everybody was encouraged that you can do it cheaper. And by the way, it's a very noble thinking. It's just not always works, not necessarily for every application. So I want to make sure people don't extrapolate whatever DeepSeek did, because it's just one model. It might be for one domain, 5 or 10 domains, but not for 100 domains. And we don't even know how the new application, what type of models you need for new type of applications, right?
Yeah. Well, and I think we almost have to, everybody has added Jevons paradox to their vocabulary last week. And so the other thing is, when we saw this play out in LED lighting, you don't actually use less energy because LED light bulbs are more efficient.
You mean like on aggregate,
more light,
right? In isolation, yes, but in aggregate, no, right?
Absolutely right. And so there's kind of that effect, and then I think we've both made points on the other applications and sort of how you deploy them also drive the thing. So I think we're in pretty good agreement there, in that the individual use cases aggregated together with their requirements for latency and kind of the customer experience, right? The client experience of what's actually happening are going to be kind of the main. And I think the other part here is really interesting, is digging in and figuring out what the big levers are.
Yes.
Right. And so that's really what this conversation's about.
In each component, you need to look what innovation is coming. It's what timelines, right? And understanding it, because it will allow you to plan better. Unfortunately, it will not be, 0 or 1. We all know, and now we know we don't need to invest in infrastructure. By the way, Ilya, I don't know if you'll agree with me, you do need to invest in physical infrastructure of energy generation and transmission. That's my takeaway, if there is something simplistic. There is a lot of it depends, but I don't think anyone could say we don't need more electric capacity. I'm just curious if you agree with that.
Yeah, so in the last decade, energy generation was pretty much flat in the US. A lot of the way that we got there is data centers got more efficient, and a lot of moving from your closet to the data center, you actually get some economies of scale, and there's some cool things there. But if we're going to deploy industrial assets in sort of the pace and quantity that we're talking about, absolutely you're going to need net new generation, and you're also going to have to think about, one way to get there is potentially transmission and kind of connect more pieces of the grid. So there's multiple ways to get there, but ultimately we're going to have to do something.
Yes, it's a great point. On demand side, I want to make sure people need to understand we barely started to deploy AI applications at scale. There is a lot of trying. That's the beauty of ChatGPT. They democratize access to try, to demo, to raise money. We are in the very early stages of scaling. There is a lot of trying and playing, but the use case that will start getting traction will start scaling like crazy. That's the beauty of modern technology. So we need to take that into account as well.
Just to recap, I think the 4Cs framework is a really good way to start to break down what the issues are in this space and really think about, understanding each column and then ultimately understanding the interplay between them. And so we're going to work really hard to bring on expertise and connect these concepts together and be able to capture and kind of paint a picture of what's happening.
Just to mention that in terms of next steps, we have very exciting speaker coming from who basically built on the compute side, and deployed, especially deployed TPUs, tensor processing units, the custom hardware that Google built to power Google Translate, Google Ads, Google Search for AI instances for many, many years at Google. And by the way, the complexities are not only develop and deploy them, but everything around it, networking, connection to grid, etc. So we are looking forward to a really good discussion on that in early March. We'll announce it on our Powering AI Stack page. And please stay tuned. It will be really exciting first episode.
Yeah, absolutely. And this conversation, this show, this discussion is really about all of us. So please send us suggestions on speakers, topics. Already in the chat here, we've had some interaction on, hey, it'd be great to break down the 4Cs into sort of the next level of detail and think about kind of what are the moving pieces. Great suggestions. Let's keep that going. We should also stay connected. So give the Powering the AI Stack LinkedIn page a follow, and then also go to the website in order to sign up for the email list. And, kind of staying connected and keeping this conversation is really how we keep moving this forward. And most importantly, thanks for your time. It's really hard to find time to engage in these conversations. We think this is an important one, and we really appreciate the folks that joined us today and actively participated in the discussion.
Yes, +1. And if you like the discussion, if you think it's an important topic, feel free to share it with your friends that are on both ends of investors, practitioners, AI operators, etc. And looking forward to seeing and interacting with all of you in our future episodes.
Absolutely. Until next time. Thanks, everybody.
Thanks, everyone.